Hello dear friends, I'm going to start with the design of the RCC bridges, reinforced concrete bridges, where it covers the few types of bridges that are slab bridges, girder and slab T-type bridges, hollow girder bridges, balanced cantilever bridges, rigid frame bridges, arch bridges and bowstring bridges. Out of these, the most commonly or frequently used type is the T-beam bridge with an effective span of 14.5 meters. The components of a T-beam bridge are the deck slab, the cantilever portion, footpaths, which includes curbs and handrails, then the longitudinal girders, cross beams or diaphragms, and the varying course. The components can be explained in the figure as well with two sections, the cross section as well as the longitudinal section. You can look upon over here. We have two things. The cross beams are shown over here. This is the, you can say, the pavement way, which is 7.5 meters. You have three longitudinal girders, 1, 2 and 3. In between them, for the few functions, we have the cross beams. This is one of the type. This is the cross section. If you go to the longitudinal section, you will see that we will have, for this 14.5 meter span, we will have 5 cross beams equally placed at 3.6 to 5 meters each. 1, 2, 3, 4 and 5 on. This is the half effective span shown to you. So this is the longitudinal section. Few more things to be discussed are regarding the curb. The width of the curb is kept from 475 to 600 mm. Varying coats are two types: asphaltic concrete having thickness 56 mm and cement concrete of M30 grade as 75 mm. Then the footpath has to be provided of 1.5 meter on the either side depending upon the location. For urban bridges we provide these footpaths, and for rural bridges we may avoid these footpaths. The cross beams are provided to serve the two functions. First one is to stiffen the girders and to reduce torsion in the exterior girders. Second is to equalize the deflections of the girders carrying heavy loading with those of the girders with less loading. For the cross beam, this has to be kept in mind when the spacing of the cross beams is less than about 1.8 times that of the longitudinal girders. The deck slab can be designed as a two-way slab. So the slab has to be designed either as a one-way slab or a two-way slab. If this satisfies, then we have to design it as a two-way slab. The designs will be discussed later on. The thickness of the cross beams should not be less than the minimum thickness of the webs of the longitudinal girders. Let us understand the design with the help of an example. Example is, we have a T-beam bridge for a rural section of a state highway. The bridge consists of 5 spans of 14.5 meter. The exposure is moderate and the cement concrete varying course has been used in this case. First step is the preliminary design. For the preliminary design, it has been shown to us that this is clear roadway is 7.5 meters. Then assuming 3 T-beams spaced at 2.5 intervals. The effective span of a T-beam will be 14.5 meters, and I have told you assuming these 5 cross beams at 3.6.25 interval. 25 grade M25 grade of concrete and Fe415 grade of steel respectively are used. The reinforcement is used as 40 mm. So this is now the numerical figure. You can see that the longitudinal girders has their spacing as 2.5 meters each from center to center. So effective span will be 2.5 minus half the thickness from this side, half the thickness from this side. The thickness of longitudinal girder is 300 and the thickness of cross beam is 250. So in that case it will be 3.625 minus 3.625 minus 0.25 by 2 minus 0.25 by 2. Then the deck slab. Second step is the deck slab. So we are going to design all the components one by one. In this chapter, in this case, I'm going to discuss only the design of the deck slab. The rest parts I will be discussed in partial videos. So first video will contain only the design of the deck slab. The slab is supported on 4 sides of the beams, and the thickness of the slab for the first case has been assumed as 215 mm. The thickness of the varying course, as already discussed, is D is 75 mm. Span in the transverse direction is 2.5 meters. So effective span will be 2.5 minus the thickness of the longitudinal girders, which gives me 2.2 meters. Similarly, span in the longitudinal direction is 3.625 meters, as discussed earlier on in the again figure. So it will be subtracted the thickness of the cross beam, which gives me 3.375 as the effective span in the longitudinal directions. Then we are going to find out the bending moments due to the dead load and the live load. For the first case, it is the maximum bending moment due to the dead load. So in dead load covers the deck slab as well as the wearing course. So weight of the deck slab, it is thickness into the unit weight of concrete, which gives me 5.375 kilonewton per meter square. Similarly, weight of wearing course, it gives me 0.075 into 25, that is 1.87 kilonewton per meter square. Total makes it to 7.25 kilonewton per meter square. The spacing of the cross beams is less than, now I have told you earlier on the how to decide for the one-way slab or a two-way slab. So this condition is, now here the spacing of the cross beams is 3.625 meters, which is always less than 4.5 meters, that is 1.8 times the spacings of the longitudinal girders. So the slab has to be designed as a two-way slab, and for this we are going to use the P-guards curves. For P-guards curves, we need to find out the ratio of the short span and the long span. So when you that value gives us the K value, which comes out to be 0.652, and 1 by K is 1.53. I have few P-guards curves. P-guard curves has given me, depending upon the values of the this ratio of K, there are some curves. So I'll show you one of the curves. We will be discussing these curves ahead. So if you look upon these are the P-guard curves for a K value of 0.4. So these P-guard curves gives us the moment coefficients m1 and m2 for a K value of 0.4. m1 is the first coefficient, moment coefficient. Second, m2 is the second coefficient. So there are one curve has two charts. So first chart, depending upon u by b, values of u by b and values of v by l, give me a value of m1, that is a coefficient m1 into 100. Similarly, for the second chart again, corresponding to u by b and v by l values, it gives me the values of m2, coefficient of m2, which is into 100. So whatever the values we are going to get from here, we are going to use as the coefficients m1 and m2 to find out the moments in the short and in the long span. We will discuss how it is. In this case of dead load, it says that when the now dead load, let me discuss give you the values of u and b. U and b are, if you look and open here, u and v are the dimensions of the load spread after allowing the dispersion on the through the deck slab. So in this case, what will be into u, we are going to find out the values of u and b, and then we're going to take the u and v, and then we're going to take the ratios of u and b and v by l. For this particular case of dead slab, there is another curve which is represented by this chart. You can look upon this chart. It says when the slab is going to be completely loaded by the UDL, then we are going to find out the corresponding values of m1 and m2 with the help of k or 1 by k. So we have already calculated the value of k or k and 1 by k, and from this k and 1 by k, we are going to find out the values of m1 and m2 from this figure 8.9 on your screen. So these are given in the appendix of the book, Johnson Victor, appendix A. So correspondingly, we get 0.047 for k 0.652 and m2 as 0.0175 for 1 by k as 1.53. The total dead load can be calculated. What we have calculated the intensity over here as 7.25 kilonewton meter square. So total dead load will be 7.25 into 2.2. This is the span between the longitudinal girders into 3.375 span between the cross-sectional girders, this cross beams. So this gives me 53.83 as the total load. Now the formulations to calculate the moments is capital M1. To calculate the moment, it can be calculated as m1, that is, you can say, take it to be the moment along the short span, is equal to m1 plus mu into m2 in brackets into p. So this gives me m1 is the coefficient we have already calculated from the corresponding value of k. m2 is the corresponding value of coefficient 1 by k. Mu is the Poisson's ratio, which is 0.15 for concrete, and P is the total load, which I have already calculated. So similarly M2 can be calculated, which is M2 which is M2 plus mu M1 into P. So the coefficients are just reversed. So this gives me for the shorter span, and this gives the moment for the longer span. So likewise we can calculate the moments. So substituting the values already calculated, we can find the moments. So moment along short span is 2.67 kilonewton meters, and against the long span we get it as 1.32 kilonewton meters. Then is the second part where we are going to calculate the live load bending moment due to we have taken up the class AA as the IRC loading, and there you know that there are two cases. One is the tracked vehicle and one is the wheeled vehicle. So first case is we are going to discuss the tracked vehicle. The size of the deck panel of the deck slab is 2.5 into 3.65 meters, which is very clear from this figure. So that panel is 2.5. This panel, it is 2.5 into 3.625. So let's say one track is going to be covered over here. So this dispersion has been calculated. Now the load dispersion is calculated by such a matter. You can see that U in terms of B and V in terms of A, and where load is dispersed like this: x plus 2d, where 2d is the thickness of the wearing course and h is the thickness of the deck slab. So this formula is given by x plus 2d whole square plus a square under the root. So this gives me the load dispersion. For load dispersion, so width of the load spread along the short span, so that means value of u 0.85. 85 is the 850 is the thickness we are talking about in this direction. So I'm going to calculate this u. So it is 0.85 as per the formula plus 2d plus 2 times the thickness of the wearing course whole square plus h is 215, so 0.215, taking care of the units, square. This gives me the value of u as 1.025 in this case. Similarly, V can be calculated. V will be in the other direction. So I have the load. Now you know that tracked vehicle has a thickness of 3.6 meters. The tank is has the length of 7.2 meters, and the contact area of this tracked vehicle is 3.6. I hope you know that. Remember what the loadings we have discussed earlier on. So accordingly, we can calculate the V values. V value comes out to be 3.756. Here it says it is limited to 3.375. As in the figure, if you look upon, the length is 3.375. So that means we cannot go beyond this length. So this is limited to 3.375 meters. Now you can calculate the K value. So K is the again the short span divided by the ratio of the long span, which gives me 0.652. U by B, U is 1.025, we have calculated over here. B is 2.2. V again we have calculated over here, limited to 3.375, and the L is 3.375. So we get V by L as 1. So corresponding to this U by B and V by L, and corresponding to K as 0.65. Now remember that K value is the P-guard curves are available for K as 0.6 and 0.7. So we can take the two values, both the values from the K as 0.6 and 0.7, and we can take the average of the values. Similarly, we find out these values as, so M1 comes out to be 7.75 and M2 comes out to be 2.7. Impact factor in this case is 25%. Total load per including, so total load will become 350 is the weight of the one track. So 350 into 1.5, total load is 437.5 kilonewton. Effective load on the span will be the total load for 3.375 divided by for 3.756, so it comes out to be 393.1 kilonewton. So this I have taken the ratio for my length. So I have length as 3.375 and it was for 3.756, so that is why I have taken the effective load. It is comes out to be 393.1 kilonewton. Moment along the short span, I have given you the formulation. It is m1 plus mu into m2 into 10 raised to minus 2. We have this value in 10 raised to into p is 393.1. so this gives me for moment along the short span for tracked vehicle as 32.06 kilometer meters. Similarly, for the longer span, I get it as 15.18 kilometer meters. So this is the first case where we have calculated the bending moment due to the live load for the tracked vehicle. Now, third case, we are going to discuss the live load bending moments due to the IRC classed wheeled vehicle. For the wheeled vehicle, the class AA wheeled vehicle should be placed on the deck slab. Let me show you the placings of the wheeled vehicle now. So this is the location of the wheeled vehicle. So first wheel has been placed very centrally over here, which is symmetrical about the y-axis as well as the x-axis. So you can look upon the load dispersion will be calculated accordingly. So I have first wheel over here, second wheel of 62.5 over here placed as per their distances. Then the third I have over here, fourth I have over here, fifth over here, sixth over here. So now the bending moments will be calculated for all these wheels. So first we are going to calculate using the P-Guards curve for the first wheel. So you see that the first wheel is symmetrically placed on both the axes, x and y axis. So hence P-Guards curve is directly applicable over here. So we need to find only the dispersion. So load dispersion, when you calculate the values of u and v, so we are talking about wheel 1. So when you calculate u, so you see that it is 0.3 plus x, the width of the load in this direction, in the direction of u, is 0.3. So 0.3 plus 2 into the thickness of the varying course plus 0.215. So using again the same formula, we get it as the load dispersion for this particular load is 0.503, v is 0.37. So we can find out now the u by b values, and v by l value. K again I have the same, it is short span upon the long span, 0.652. For this values I can find out the use the P-Guards curves, and I can find the values m1 and m2. And when you take the total impact load in this case is 25% for the impact. The load value is 62.5. So 62.5 into 1.25 gives me 78.1 kilonewton. Moment along the short span m1 plus mu m2 into this load. So this gives me 16.5 kilonewton meters. And second case for the long span, it gives me 13.6 kilonewton for the calculations. So this is first wheel load. Likewise, we will calculate for the all 6, and then we will add up to have the total bending moment, total live load bending moment due to all the wheels. Now for wheel number 2, you see that for wheel number 2, forget all the other wheels. We have only to consider the wheel number 2. So you see that it is symmetrical to x-axis, but it is not symmetric to y-axis. So the P-Guards curves are directly not applicable in this case. So to that, I'll show you one figure. Look at over here. Just here over here. So here what you see is what we have done. We have chosen the real load of 62.5 kilonewton over here, and we have placed one dummy load of 62.5 kilonewton of the same intensity over here on the same location. Real load and the dummy load. So what we are going to use is we are going to take the whole strip of this dispersion of 375, and then we will calculate the load for the load symmetric to y-axis. So when you consider this whole strip, that will be symmetric to y-axis as well as the x-axis. So if you consider this total load and you find out the bending moments, and then you consider only this load which is in between the two, this strip, assuming that the load is in between these two, then what we can do is we can subtract the second value from the first and just take it half of that, and you'll get the results for this case. So let us see how we have done these calculations. So intensity of the load is, again, it is 62.5 into 1.25, that is the impact factor, divided by 0.503, 0.375, this is the load dispersion. So I get this value as 414.2 kilonewton per meter square. So considering, as I told you, we will take it in two parts. First we will consider the whole strip which is to be loaded. So the whole strip, if it is loaded, is of 2.2 meters into 0.3 into 2.2 into 0.375 meters. So for that I get m value, m1 as 8.25 and m2 as 8 into 8 into 10 to the minus 2. So I can calculate the moments using these strips. So moment along short span gives me 32.29 kilometer, and against the long span it is 31.56. So you can look upon the calculations what I have done over here. Then, as I have told you, then I am going to consider the dummy area, the area between the real load and the dummy load. So that this distance gives me, if I subtract, you look upon this figure. Now what I have done, I have subtracted 352 and 352 from 2.2 as in total. So this gives me 1496. So that means my strip is of now 1.496 and into 0.375. So I have done all these calculations again for that. For that I got m1 as this and m2 as this value from the P-Guards curves. Again I can calculate these moments, moment along the short span, moment along the long span. So net bending moment, which will my resultant will be the moment calculated for the whole strip minus this for the area between the real and the dummy load by 2. I have taken the dummy load, so dummy load will be removed. So this gives me a result of 2.2 kilonewton meters as the bending moment along the short span for actual real load of 62.5, which is placed asymmetrically. Similarly, for the long span, it is 2.751 kilonewton meters. Likewise, we will do the calculations for the wheel 3 and wheel 4 and wheel 5 and 6. So for wheel 3, let me show you the load placement. So wheel 3 is placed like this. So again, we see that wheel 3 is asymmetrically placed. The real load is such like that. I have placed a dummy load over here. We will take first the full strip, we will find out the values, and then we will take the area between the area where the load is not there, this one and this portion and this portion. So we will subtract that and divide it by 2 to get the actual result. So the calculations, you can see that intensity of the loading in this case will be 37.5. The load is 37.5 into 1.25 divided by the load dispersion area. So considering the loaded area 2.2, that was the fully area. For this area you can calculate the u by b values. So u by b will be 2.2 by 2.21 and this is 0.11, k again 6.652. You can calculate the values of m1 and m2, and hence you can calculate the values of the moments along the long span and the short span and the long span. Now we will consider the area which is non-loaded symmetric. Now considering the non-loaded symmetrical area for the imaginary loading. So loaded area now becomes my 2.2 minus 0.503 minus 0.503. This gives me 1.194. For this I have done again the calculations and calculated the moments. So net bending moments will be the moment calculated earlier minus this by 2. So I get the net results as 1.68 kilonewton meters and 1.5 for the short and the long span respectively. Similarly, now you see that for wheel 4, when you go to wheel 4, so this is just disposition of the wheel load 4. 62.5 Newton is now placed symmetrically to y-axis but not to asymmetric to the x-axis. So we will consider this strip over here. So this strip is of 1687.5 plus 1687.5. So you have to do the calculations accordingly. So and hence we will take the bending moment for the whole strip, then we will take for the area between these two and subtract and divide it by 2. So we will get the values for 62.5 kilonewton placed over here. So this is disposition of the load wheel 4. Similarly we will do it for the wheel 5 and wheel 6. Now you can look upon the wheel 5 is asymmetric to both x and y axis. Similarly, wheel 6 is asymmetric to both x and y axis. So one of the axes can be taken up which you feel comfortable for the calculations. So here it has been taken the case as where it is asymmetric to x axis. So y axis has been considered on. So likewise you can calculate the values of bending moments for wheel 4, then wheel 5, and hence you can calculate the values for wheel 6. You can look upon this. These calculations you have to need to do. Then total bending moment will be, you can add all these, so we get these values as 27.63. so all the values for all the wheels have been added and we get these moments. So now whatever the moments, now we have to compare this with the tracked vehicle. So in the case of the tracked vehicle, we have found this the bending moments along the short span is 32.04. You can go back. So for the tracked vehicle, we have calculated this bending moment as 32.06, and similarly for long span it is 15.18. So this is critical in our case, so we will use that values. So when you for the design moments, it says to maintain the continuity, the design bending moments will be total bending moment due to the dead load plus bending moment due to the live load into 0.8. 0.8 has been used to maintain the continuity of the beams of the slabs. So the design moments are 27.7 and 22.13 along the short span and long span respectively. Now we can calculate the reinforcements. The bending stress is 8.3. This is in the steel, it is 200 200 MPa. J value is 0.9, you all know this. R is 1.1. So effective depth required is 27.7. The critical among these two, 27.7 into 10 per 6 by R, that is 1.1 into per meter. So this gives me a value of 158.88 meters, which may be taken approximately to 160 meters. The effective depth what we have provided for 12 mm diameter, it is 215 minus the cover minus half the diameter. So this gives me 169 mm. Similarly, so 169 is always greater than 160, hence we are safe for the section. Steel can be provided as per our case m by sigma st into j into d. So you can calculate this value. You provide 12 mm dia bars at the rate 110 mm, so ast provided is 1028 mm square. Similarly, you can provide the steel for the other case for the longitudinal reinforcement. Their critical bending moment will be 22.13, and hence you can provide the steel. Effective depth in this case will be 215 minus the cover minus 1 bar of the steel minus half the bar of the steel in the other direction. So it is 157 mm. So you can provide 12 mm bars at the rate 150 mm center to center, and the AST provided is 808 mm square. So this covers the one part of the design which we have, the design of the deck slab. The other designs I'll be taking in the other classes, other videos. So keep tuning. Thank you.